Hello everyone, welcome back to Physics 331. Today what I want to do is I want to start discussing transmission lines. Transmission lines are made up of a pair of conductors where the geometry of the conductors doesn't change along the length. A common example is a coaxial cable, which is something we use in the 331 lab all the time. And in a coaxial conductor, what you have is an outer conductor that is concentric with an inner conductor. And so the inner conductor maybe has radius R1 and the outer conductor has R2. Another geometry of transmission lines is just if you go outside and look at the hydro poles, there's two long conductors strung up side by side. And so for the purposes of this discussion, maybe that's what we'll have in mind just because it's easy to draw. So we're going to imagine perhaps a voltage source and then a switch, and then we're going to connect them to a set of parallel conductors. And so these conductors will have some length L. And what we're going to try to do is we're going to try to understand some of the properties of transmission lines in general. And in fact, we're going to find that even though the geometry is incredibly simple, that they can actually be quite rich in physics and lead to some complex behavior. So we'll also define a z-axis, which the transmission line is parallel to. So the conductors are parallel to the z-axis. So what I want to imagine is that we close the switch. So when the switch closes, if we start with conductors that have no charge, no potential difference, after closing the switch and waiting a very short time, we'll develop a potential difference across these wires. So when the switch closes, we get a potential difference across these wires or conductors. And so in fact the conductors will be charged as well, and what you could do is you could take the ratio of the charge on the conductors to the potential difference across them, and that by definition defines capacitance. So our wires charge, and that means that there is some kind of effective capacitance. That's not so hard to imagine. When we think of a capacitor, we think of a parallel plate capacitor. So we have a set of parallel conductors, and we can calculate the capacitance. So here we have parallel conductors. Maybe the geometry is a little bit different, but it's not hard to imagine that there's some capacitance associated with this geometry, right? And so C, remember the way you calculate C is take the charge and divide by the potential difference. Okay. Now, if initially our conductors were uncharged, then there must have been some kind of transient current to deliver the charge to the wires. And whenever you have a transient current, a current that changes with time, then you can associate as an inductance with whatever your experimental setup, your circuit is. So there must be a transient charge, a transient current, I should say, to transport the charge so that the wires actually charge up. And so that's going to lead to some kind of effective inductance associated with this geometry, with our transmission line. So maybe if you recall that the voltage across an inductor is equal to the inductance times the time derivative of the current. Okay, and so we have a current that's changing with time, so we would get a non-zero di by dt. If we take the voltage across our inductance or whatever it is we're studying and divide it by that di dt, then that will tell us what the effective inductance is. Okay, for simple geometries, we can actually calculate what the capacitance and the inductance are. So let's suppose we have parallel wires, and now I'm going to draw this in a little more detail. So we'll have parallel wires where the radius of the wires is A, and we'll separate them by some distance d, and let's assume that the separation distance d is much greater than the radius A. Well, what you can do is you can calculate the electric field. So let's see. We can use Gauss's law to calculate the electric field. Gauss's law is Q enclosed over epsilon naught is equal to the integral of E dot dA, where you would have to define some kind of Gaussian surface. Then once you have that electric field, you could calculate the potential difference using E dot dl, the line integral of the electric field. And so once you've calculated that potential difference, it's going to be proportional to the charge on the wires, and that allows you to calculate the ratio Q over delta V, which will lead to the capacitance. And for these parallel conductors, let's say of length L, I'm going to leave it to you for an exercise to do that calculation. And what you should find is that the capacitance per unit length, which I'll denote as C sub L, comes out to be pi times epsilon naught divided by the ln of d over A. And so what you can see is that this capacitance per unit length is just determined by some constants, pi and epsilon naught, and the geometry of the wires. And so if you change either A or D, you can adjust the capacitance per unit length. Well, you can do something similar for the inductance. You would use the integral of B dot dl is equal to mu naught I enclosed. So I think that's Ampere's law, right? So that tells you the magnetic field. And once you know the magnetic field, you could calculate the magnetic flux, which is B dot dA. And then by Faraday's law, once you have the magnetic flux, the time derivative of the magnetic flux tells you the induced EMF, or equivalently, the voltage across your inductor is going to be determined by the time derivative of this magnetic flux, which you're going to set equal to L di dt, which then allows you to solve for the inductance. Again, this is a good exercise to try. If you do it, you should find that for our length of parallel conductors, of parallel wires, the inductance per unit length, which we'll denote L sub L, is equal to mu naught over pi ln d over A. Again, it's just constants and geometrical factors that determines this inductance. So what that leads us to do is to say, well, okay, we have these simple parallel wires. We have determined what their effective capacitance and inductance are, and so we can come up with a model for a circuit model for these parallel wires. So if we go back to our starting point, we had a battery and a switch, and then connected to some parallel wires of a certain length. And what we're going to do is we're going to say, okay, let me model that as a battery and a switch. And then we'll have a series inductance and a capacitance in parallel with the output. So we put the capacitance in parallel with the output because that's going to determine the difference in charge across these wires after the switch has been closed. And we have a series inductance because that's going to control how the current evolves with time, the time dependence of the current. And so this is our simple circuit model of parallel wires. So if the length of our parallel wires was L, then this inductance, the total inductance, would be the inductance per unit length times L, and the capacitance would be the capacitance per unit length times L. Okay, so that's good. What I want to think about now is the case where we have the same type of geometry, except we make our transmission line, our parallel wires, really long. So if the wires are very long, what we could do is have our battery and switch, and now we have like a really long wire. And maybe what we're going to do is we're going to close the switch at time t equals 0, and we've set up a situation where we're going to measure the voltage along the wires. So maybe the voltage difference between this wire and the top wire and the bottom wire at a bunch of different points. And we'll make those voltage measurements at a time t after the switch has been closed. And if that time t is a very short time after the switch is closed, we'll find that these voltages are not all the same, right? Obviously, we would expect, I think, the voltage closest to the battery, V1, would be larger than the voltage far away from the battery at, say, V5, a very short time after closing the switch. If we wait a really long time, then our wires will charge to an equilibrium and all those voltages will come to the same value. But let's think about this short time. So we would expect V1 not equal to V2, not equal to V3, and so on. In fact, we could have probably said V1 greater than V2 greater than V3 a short time after the switch is closed. Well, that kind of behavior is not going to be captured by this simple model, because what we would require is that the voltage anywhere to the right of the inductor would always have to be the same, right? Because the only components that we have in our model are a single inductor and a single capacitor. So in that case, this so-called, what we might call is a discrete or lumped circuit model of our parallel wires fails when the conductors are long. And so you might say long compared to what? And so I think that's a question that we'll try to answer maybe in the next video. Okay, so what we're going to do is we're going to come up with what's called a distributed model. So we're going to model the long transmission line as a distributed LC network. And so really what that means is we're going to take each one of these, say, short little lengths. Maybe this is a length of, say, delta Z, and maybe all of these lengths are delta Z. And we're going to say, well, the model we came up with works pretty well for these short little sections. And so why don't we use the LC model for each little section, and then we'll just cascade a whole bunch of them one after another. We'll daisy chain them. Okay, and what that looks like is, here's our switch. And so the first little section of transmission line has an inductance and a capacitance. And then we measure V1 here. And then the next little section has an identical inductance and capacitance. And now that we have additional components in our model, we can have different voltages at these different points. So here's V3. And we can just keep going. So here would be V4. And you just keep going with this type of model. Okay, so in this case, the inductance of each of these inductors would be the inductance per unit length for the geometry that we chose. Notice that we didn't do this calculation, but let me go back here. The inductance per unit length, when we divide by the length, the L doesn't appear in this expression here. Same thing for the capacitance per unit length. When we divide by the length, there's no L in this expression. So each one of these little LC branches has the same inductance per unit length and the same capacitance per unit length. And then if we multiply by the delta Z, the length of each branch, that tells us the inductance of each of these inductors, and likewise the capacitance of each of the capacitors is the capacitance per unit length times delta Z, the length of that branch. Okay, so what we're going to do now is isolate one of these branches and do a bit of a circuit analysis on it and see where it leads us. So we consider one branch of our distributed model. And so what it's going to look like is we have our inductor and we have our capacitor. And what we'll say is over here, we're going to have a voltage at the left side at, say, position Z and time t. And likewise, we'll have some current at position Z and time t. Okay, and then over here on the right-hand side of our LC network, we'll have advanced at position delta Z. And so now what we have is a current at position Z plus delta Z, and it's also going to be potentially time dependent. And the voltage at this output is at position Z plus delta Z, and it is a function of time. Okay. So what we're going to do, first of all, is just a Kirchhoff voltage loop analysis. So we'll start here on the right-hand side where the voltage is V of ZT. And then let's do a clockwise loop. So I'm imagining we start here and then we do a bit of a loop. And so we'll cross this inductor. And so the voltage dropped across the inductor is the inductance, which is the inductance per unit length times delta Z, the length of the branch. And then remember it was di dt. So it's di, which is a function of zt, dt. And then when we do that, that takes us to this node here where the voltage is V of Z plus delta Z and t. So that should be equal to V of Z plus delta Z and t. Okay, good. So we can do a bit of rearranging. Let's write it like this. We're going to write v of z plus delta z t. So that's on the right-hand side of the equation above. We'll subtract off the v of zt and then divide by delta z. And what's left over is the minus the inductance per unit length di by dt. But of course, in the limit that the length of each one of our little branches is short, in the limit that delta z goes to 0, this left-hand side is by definition the position derivative of the voltage. And so what we have then is dv of zt dz is equal to minus the inductance per unit length di dt. So we have a partial differential equation where we have a derivative with respect to z on one side, a position derivative of the voltage, and on the other side we have a current derivative with respect to time. Okay, and so this is going to be equation 1. You might be able to guess what we're going to do next. We've done a Kirchhoff voltage loop, and so now we're going to do the Kirchhoff junction rule. Okay, so let's go back and look at this picture. So we have a current I of zt going into the junction, the top junction let's look at, and then we have a current I at z plus delta z going out of the junction, and we would also have a current going through our capacitor, and so maybe I'll call that IC. Okay, now let's just remind ourselves that capacitance is Q over delta VC, say the voltage across a capacitor, and so that means Q is C times delta VC. So if we wanted the current in the capacitor, that's going to be dq dt, which is going to be equal to C, and then it's going to be dvc dt. Okay, so with that in mind, let's do the junction rule. So the currents into the junction equals the currents out of the junction. Going into the junction, we have I at position Z. So we have I zt is equal to the current leaving the junction, and so we have let's see, the capacitance. We have a capacitance per unit length times delta Z, so that's the value of the capacitance. And then we have the voltage across this capacitor is equal to the voltage at the output, which is V of Z plus delta Z. And so we have dV Z plus delta Z. It's also a function of time, and it's dt. And to complete the junction rule, we also have the current I at Z plus delta Z leaving the junction. So then we have plus I Z plus delta Z t. Okay, like we did before, we'll do some rearranging. So I'm going to end up with an I at Z plus delta Z minus I of Z, and then we'll divide by delta Z. So what we have is I Z plus delta Z minus I at Z, and then we divide by the delta Z, Let's see, if we do that, then we're going to have to subtract off the capacitance term, so we'll get a minus CL. We've already divided by delta Z, and then we have a dVZ plus delta Z, and it's a time derivative. It's a derivative with respect to time. Okay, then we take the limit that delta Z goes to 0. And so two things happen. First, on the left-hand side, the difference in currents divided by delta Z defines the position derivative of the current. So we end up with a dI zt dz. And then we take the limit that delta Z goes to 0, then this is just going to go to 0. So then we have remaining just the minus the capacitance per unit length times dV dt. Okay, good. And so this is equation 2. So we have these two first order partial differential equations. And what we'd like to do is to see if we could make some progress in kind of manipulating these further. And so to do that, we're going to make some assumptions. So the first assumption is, let's assume that the voltage and current are harmonic functions. That just means that they're like sinusoidal functions. So we can assume that the voltage, which is a function of position and time, is going to equal some amplitude, which is position dependent. And then all the time dependence occurs in the e to the j omega t. So this is like a sinusoidally oscillating signal, and the frequency of oscillations is omega, and all the position dependence is in the amplitude. And so likewise, the current is going to have the same kind of form, position dependent amplitude, and then the time dependence is in the e to the j omega t. Okay. The reason that this is a useful assumption, really there's two reasons. One is when we're using transmission lines in, say, a physics experiment, it's very often the case that we are dealing with sinusoidal signals. So it's a case we encounter very often. The other thing it's going to do, it's going to allow us to actually evaluate the time derivatives in equations 1 and 2. So in equation 1, we have a time derivative of the current on the right-hand side, and in equation 2, we have a time derivative of the voltage on the right-hand side. And so if all of our time dependence is in the e to the j omega t, then we can easily evaluate those time derivatives. Okay, so specifically from equation 1, let's just go back and look at it. There's nothing we can do with the left-hand side because that's a position derivative, and we haven't said anything about the form of the dependence of the amplitude on position. So what we'll have is a d by dz of v of z e to the j omega t. Okay, so that is the left-hand side. On the right-hand side, we have the minus the inductance per unit length times the time derivative of the current. So that's equal to minus the inductance per unit length. And let's just do this in a lot of detail just to start. So we have a position dependent amplitude, and then we have e to the j omega t. Okay. Well, what we could do is, we could say, for the left-hand side, the position derivative acts only on the amplitude, and then we just have e to the j omega t left over. But on the right-hand side, we can actually do this derivative. So we get minus, when we do the derivative, we get a j omega coming down. Then we'll still have the inductance per unit length. And we'll still have our amplitude. I'll drop the explicit position dependence for now. And then we have e to the j omega t. And what's nice is we've got the e to the j omega t on both sides, which we could cancel. And so now we have an expression that involves only position. So the amplitudes are position dependent. The time dependence is completely gone. Okay, and so what we've got then is that dv dz is equal to minus j omega inductance per unit length times I. In fact, I'm gonna label this equation because we're going to make use of it again, possibly in the next video. Okay, so that's from equation 1. So from equation 2, you can imagine that the exact same thing's going to happen. We're going to have a di dz, which we can't do anything with except separate out the e to the j omega t. So we'll end up with a di dz e to the j omega t is equal to, and on the right hand side we have minus the capacitance per unit length and then a time derivative of the voltage. That time derivative is going to bring down a j omega. We're going to have the capacitance per unit length, and then we're going to have the voltage amplitude and e to the j omega t. And once again, we cancel out the e to the j omega t, so all the time dependence is gone. And we're left with di dz is equal to minus j omega capacitance per unit length times the voltage. Okay. So what's nice here is that we can do a further manipulation. And so let's go back up here to the equation in the blue box. Let's take a second derivative with respect to position. So then we would get d2v dz2 is equal to minus j omega inductance per unit length di dz. Okay, maybe you can see what we're going to do. We're going to take this di dz and we're going to sub it into here. Okay. We can do the same thing to the second equation. We'll take another position derivative. d2I dz2 is equal to minus j omega capacitance per unit length dv dz. Okay, and then we can take the dv dz in the blue box and we can sub it into here. Okay, let's do that. So we'll start with the first equation. So I'll try to draw it right here. So d2v dz2 is equal to minus j omega inductance per unit length. And then for di dz, we're going to use minus j omega capacitance per unit length times voltage. And we can simplify that a little bit. We have a minus sign times a minus sign, which is positive, but then we have j squared, which gives us a minus 1. So we get minus, we have two factors of omega, so we get minus omega squared, and then we have the inductance per unit length times the capacitance per unit length times the voltage. This is really nice because now what we previously had was equations that mixed voltage and current. Okay, we've gotten rid of the time dependence, which was a nice first step, but now with the substitution that we've just made, we've ended up with a differential equation that depends only on voltage. We've removed all of the current dependence. And so that only works for this harmonic assumption that we've made. All right, we could do the same thing with the second equation. We could say d2i dz2 is equal to minus j omega capacitance per unit length. And then we have to look up dv dz from above, from the number sign equation. It's minus j omega L times I. So it's minus j omega inductance per unit length times I. And so we do the same sort of simplifications, and we get d2i dz2 is equal to minus omega squared inductance per unit length, capacitance per unit length times the current. And so this has the exact same form as a voltage equation. It's just it's in terms of the current. So these two expressions, you've probably seen these before. These are referred to as the wave equations. I mean, and that's kind of one of the most, like, an early kind of surprising thing. Like, all we started to think about was a set of parallel wires, and we came up with a circuit model for it, and, you know, making some assumptions, we've ended up at the wave equations, which is perhaps a bit of a surprise. Okay, so what we're going to do is we're going to try to guess a solution to these wave equations. What we need is something when, like, if we look at the voltage equation, we take two position derivatives of the voltage, and then we get the voltage back again times a constant with a negative sign. So when we think of taking derivatives and getting the same function back again, that leads you to think of exponentials. And so if we take two derivatives of an exponential, how are we going to pick up a negative sign if there's a j, the complex number j, inside the exponential? Then when we take the two derivatives, we'll get two factors of j coming down. We'll get j squared, and that will produce a negative sign. So the general solution to the voltage equation, I mean, it's a general solution to the current equation as well, but let's think about the voltage equation is the voltage amplitude. So remember, this was just the amplitude of a sinusoidal voltage, and it depended on z, is equal to some coefficient that I'm going to write as z plus. We'll see why I chose z plus in just a few moments, I think. J beta z, beta is some constant, plus some other coefficient. I'm going to choose v minus for that coefficient, e to the plus j beta z. Let's just verify that actually is a solution to our wave equation. So we need to take two derivatives of v. So the first derivative is going to be minus j beta v plus e to the minus j beta z. And then we're going to get plus j beta v minus e to the j beta z. So that's the first derivative. In fact, I think we're going to use this equation in the next video, so I'm going to label it now. We had an equation number sign above. Let's just, looking ahead, number sign was an equation for the position derivative of the voltage amplitude. And now equation star is also a position derivative of the voltage amplitude. So equation, number sign, and star must be equal to each other, and we're going to make use of that fact a little later. But let's go back to what we're trying to do. We're trying to verify that this assumed solution was a valid solution to the wave equation. And we need to take two derivatives. So let's take the second derivative now. Let's see. So we're going to get, when we take the second derivative, we'll get j squared beta squared v plus e to the minus j beta z. And then we'll get plus j squared beta squared v minus e to the j beta z, which is equal to, the j squared is going to be minus 1, so we'll get minus, and then we have beta squared in both terms, so we can factor that out. So we have minus beta squared v plus e to the minus j beta z plus v minus e to the j beta z. But everything in the brackets there is just exactly what we assumed for our solution. So this is the voltage amplitude, and lo and behold, that two derivatives of v with respect to z is equal to minus a constant times the voltage back again. And so that's our wave equation. Wave equation. Okay, and so our wave equation was this form, and so it was minus omega squared, the inductance per unit length times the capacitance per unit length times voltage. And so our assumed solution is valid provided that beta squared equals the omega squared inductance per unit length times capacitance per unit length. So our assumed solution is valid provided that beta squared is equal to omega squared times the inductance per unit length times the capacitance per unit length. Or in other words, beta is equal to omega times the square root of the inductance times capacitance. Okay, good. So what I'd like to do, as I think the last thing we'll do in this current video, is to try to come up with an interpretation of the two terms in our assumed solution. We had one with like a v plus coefficient and one with a v minus coefficient. And so let's see if we can understand the meanings of these two terms and perhaps also understand why I've chosen v plus and v minus for the symbols to use as the two coefficients. Okay, so the full time-dependent voltage, is given by V is equal to the voltage amplitude times e to the j omega t. And now we have a solution for that full voltage amplitude. It's V plus e to the minus j beta z plus v minus e to the plus j beta z, and then times e to the j omega t. And so if we simplify this, or I don't know if it's simplifying, but if we combine the exponentials, we'll get v plus e to the j, and then we have omega t minus beta z, and then we have plus v minus e to the j omega t, and this one's a plus beta z for the second term. You might recognize this form of e to the j omega t plus or minus beta z as a traveling wave. And so let's see if we can interpret these traveling waves a little bit. So we'll do our interpretation by considering, let's consider sine of omega t minus beta z. Okay, so you know that this complex exponential e to the jx could be written as cosine x plus j sine x. So it's related to, these complex exponentials are related in an intimate way to trig functions. So what we'll do is we'll make a plot. We're going to make a plot as a function of z, and on the y-axis we'll put sine omega t minus beta z. And so we'll pick some time. Let's say we pick a time t1, and at t1 our sinusoidal wave looks something like this. And so this is time t1, and we're plotting this as a function of z, and let's suppose that over here is some position z1, and at this time t1 and this position z1, our sine function is going through a maximum. And then we wait a small amount of time later, and a small time later our function's a little bit different because omega t, the omega t value inside the argument is changed because t is changed from t1 to t2. And so we get a different sine wave. And maybe it looks like this. It just shifted perhaps to the right. And so this is at some later time t2. And, you know, the sine wave goes through a maximum at some new position z2. Okay. But at time t1 and z1, the sine function is at its maximum value, and at time t2, z2, the sine function is also at its maximum value. And so these two functions are equal to each other if we set t1 and z1 equal to in one of the functions, and t and z equal to z2 and t2. So in other words, we must have that sine of omega t1 minus beta z1 is equal to sine of omega t2 minus beta z2. Right? We just look at the graph and we see that the sine function is equal at these sets of parameters. And so the only way this is equal, these two sine functions are equal, if their arguments are equal, you know, to within a factor of 2 pi. So we'll say omega t1 minus beta z1 must be equal to omega t2 minus beta z2. Okay, so let's do some rearranging. Let's collect omega terms. And so if we have omega t2 minus t1 on one side of the equation, then on the other side we'll have a beta. And let's see, we're going to have a beta z2 minus z1. So we're going to take the z2 over to the left-hand side in the top equation here. Okay, but t2 minus t1 is just a change in time, and z2 minus z1 is a change in position. And so that must mean that, let's see, omega divided by beta is equal to delta z divided by delta t. But delta z over delta t is just the speed. So I'm going to use S for the speed. I'm not going to use V because that would be confusing with the voltage. And so S is the speed. And let's note that this is positive. It's greater than 0. So what that means is that the e to the j omega t minus beta z, so we just analyzed the minus beta z case, corresponds to a traveling wave propagating along the positive z direction. So this represents a signal propagating along the positive z direction with a speed s is equal to omega over beta. Okay, we could have done the exact same type of analysis for the omega t plus beta z case, and what we would have found is that e to the j omega t plus beta z would represent a signal propagating along the minus z direction with the same speed, if you go through the analysis, equal to omega beta. Good. So I think if we go back here and look at our solution, we picked these coefficients v plus, multiplying the e to the minus j beta z. And so the v plus indicates that this corresponds to signals propagating in the positive z direction. And the v minus indicates that the e to the j beta z with the positive sign in the exponential corresponds to a signal propagating in the negative z direction. All right, only one more thing that I want to do. Remember, we said that our solution was valid provided that beta was equal to omega times the square root of L times C. Okay, so let's think about this speed that we calculated. So S is equal to omega over beta, and we said that beta, to be a solution to the wave equation, had to be omega times the square root of the inductance per unit length times the capacitance per unit length. So of course the omegas cancel, and so we get 1 over the square root of the inductance per unit length times the capacitance per unit length. So this is our propagation speed. Okay, so that's interesting because if we think back to the very beginning of the video, we were thinking about the geometry of a pair of parallel wires. The wires had radius A and they were separated by distance D. And we wrote down some expressions for these parameters, the inductance per unit length and the capacitance per unit length. And what we found is that they were determined just by these geometrical factors. In fact, let's go all the way back and let's look at that. So here's the capacitance per unit length and the inductance per unit length. So pi times epsilon naught divided by the ln of d over a, and then we have mu naught over pi times the ln of d over a. So let's put that in and see what happens for our propagation speed. Okay, so for parallel wires in free space, recall that, let's see, capacitance per unit length was equal to, oh shoot, I already forget. Let me look it up here. It was pi times epsilon naught divided by ln of d over a, and the inductance per unit length was equal to mu naught divided by pi times the ln of d over a. So our propagation speed involves the product of these two things. So the inductance per unit length times the capacitance per unit length. The ln factors cancel out. So it's kind of interesting. It doesn't matter what the distance between the conductors are or what the radius of the conductors are. The factors of pi cancel, and we get epsilon naught times mu naught. But you may know that the permittivity of free space and the permeability of free space, when you take their product, gives you 1 over the square of the speed of light. And so that's 1 over c squared. C is the speed of light in vacuum. And so therefore our propagation speed S equals 1 over the square root of the inductance per unit length times the capacitance per unit length is just equal to C. Okay, good. So that's where I want to stop for this video. But we've done a lot, right? We started with just parallel wires, and it's amazing that through kind of a, maybe a in-depth analysis, but one that's not overly complicated, we've come up with the wave equation, we wrote down the solution, we interpreted that we would have signals propagating along positive Z and negative Z, and we've calculated the propagation speed and found it to be exactly equal to the speed of light. So that's kind of interesting. We're going to do some more in the next video, and so I will see you then. Thank you very much.